All right, we're gonna start on. So, thanks everybody. I hope it's not a big crowd hanging out west side door there, but I did hang a poster over there, so they'll be coming around a little late. They show up over there, but we got a nice new room tonight, so that'll be extra comfortable as we kind of mix things up with our agenda. Begin with a presentation here in just a moment, and then kind of do everything in reverse order, finish up the evening. So I'm going to introduce our guest speaker tonight. Michael Solontoi is an associate professor of physics at Monmouth College. His main professional astronomy work focuses on an understanding of the relative populations of asteroids, comets, and solar systems, all at the Vera Rubin Observatory. I finished his doctorate at the University of Washington, Seattle in 2010 and ran his planetarium there and was the Ask an Astronomer scientist on the floor of the museum at the Adler Planetarium in Chicago while doing his postdoctoral research fellowship. So he certainly has worked with folks of all ages in astronomy. His strong involvement in public science astronomy includes giving regular talks on a variety of subjects at observatory and public science events for a wide variety of audiences across the country. So with that, I'm going to stop sharing. And hopefully the mics are working.
Yeah. Is it still working?
It's still working.
It's still working. Step one. All right. Well, and share. And we should see a big screen now.
Yes, we do.
Outstanding. Everything's still working. So thank you for the introduction and thanks for having me here. I'm really excited to be talking about this project. The Vera Rubin Observatory and the forthcoming Legacy Survey of Space and Time, which I have to say is a really cleverly named acronym, because up until the point that we were an officially named NSF, National Science Foundation facility, the program was the Large Synoptic Survey Telescope. So by calling the survey something with the same abbreviation, we got to keep all of our logo merch and things like that. So that was pretty clever. But this is a project that's near and dear. I started working on what is now the Rubin Observatory back 20 years ago. I remember sitting in my PhD advisor's office talking about this new telescope idea that was still being developed. So we're going to talk about the Vera Rubin Observatory, as I call it, Adventures with the Big Telescope. So, and this kind of tells you that I am not super duper serious. So I'm not super duper serious. I like to have a good time and chat. I will warn you, I'm not used to giving a talk sitting down, and it's allergy season. So if I bobble a number, be nice. I'm not, so anyhow.
I'm going to have you pause for a second.
Oh, you bet.
Change the resolution of the main screen here. Our side screens are fine.
Oh, okay.
See, the main screen is not as good as the
Uh-oh. Not a problem.
Let's see if I can do that here. Yeah. Okay, let's. I did not.
Uh-oh.
The projector needs to like be adjusted somehow, so I don't know if we go to.
Let me try one more time. We had it figured out.
Yeah.
Back here.
Very quick and we'll go back.
Okay, try. Let's see if I got a scroll.
You want me to exit out and stop the share?
Why don't you stop sharing and come back in and see what we got?
You betcha. So let me go ahead and actually just, we'll do that. We'll do this. Yes. Second. Minimize this down again. Yoink. And let's try this again. Screen to share.
Randy, the left side of the projector is off on this side.
I think we can run with that.
We can run with this? All right.
Yeah. All right.
Fantastic. So to kind of give a theme to what I'm going to be talking about here, I like this quote by Proust, which is only a pseudo quote, because if you really go hunting for it, it's a little bit different, but everybody rolls with this version of the quote. The real voyage of discovery consists not in seeking new landscapes, but in having new eyes. And that's kind of the idea I want folks to think about it, is that the Vera Rubin Observatory is a new eye. It's a new way of seeing things. And we're going to talk a little bit about astronomy and astronomy surveys in the concept of having new eyes. And we'll spend the bulk of the time talking about the topic at hand, which is the Vera C. Rubin Observatory, and as well as what it really means for the future of astronomy. The Vera C. Rubin Observatory is going to be producing data in such a volume that we are fundamentally going to need to think differently about how we do astronomy moving forward. But first off, back to eyes. As long as there have been human beings with human eyes, people have looked at the sky. We can kind of argue whether astronomy was kind of the first science or the second science. It was either astronomy or medicine. It was when our great ancestors either did they look up and ask what was the sky, or did they ask why did the red berries make them sick first? You know, it's just kind of which question they asked first. But for as long as people have been around, we've done an astounding job with our human eyes of looking at the night sky and seeing everything there is to see. We mapped our mythologies and our religions to the sky. We use the sky as our calendar, our clock, our entertainment. I mean, Netflix was far off at that time, so it was the only thing to watch at night. And people did an amazing job. But you can only see the light that your eye can collect. And this changed in the 1600s with the telescope. And the telescope is a new eye. I mean, not literally an eye, you're still using your human eye, but now when you look through a telescope, you're not limiting the light that's approaching you through your pupil, but however much light the telescope collects, or as I refer to telescopes, it's a light bucket. You're not collecting a big bucket full of light. Most notably, Galileo pointed a very early telescope at the sky and saw things that no one before him had ever seen. He had a new eye. He was looking with new eyes. He saw craters on the moon. He saw mountains on the moon. When he looked at fields of stars, he saw innumerable stars that no one else had ever recorded. He saw phases of Venus, and perhaps most famously, he observed 4 little teeny tiny stars dancing back and forth across the planet Jupiter, which today we know as the 4 largest moons of Jupiter, Io, Europa, Ganymede, and Callisto, which are now known as the Galilean moons. Galileo himself wanted to name them the Medicean stars because he was trying to butter up to the Medicis for, research funding. I mean, some things never change. So the next eye that we get in astronomy is the photograph. We have the ability to photographically record things. And I'm using photograph very loosely. Yes, John Draper in 1840 produced what is probably the first very loosely, I can't pronounce this, daguerreotype, image of the moon. That's it right there below him. It's in pretty bad shape. But that's not too bad considering it was thought to be lost for about a century. His son really took astrophotography into something that one does. And in 1880, he has that image there of the Orion Nebula. And then in 1882 is the Orion Nebula again. And, that looks like the Orion Nebula. He really had it down. And what the film was able to do is it's another type of new eye. Number one, it lets us break from the idea that you look through the telescope and you have to draw. So it prevents us from only being astronomers if you could draw really well, which is good for me because I draw like an arthritic gibbon. Just ask my students. It's horrifying. But in addition to getting this beautiful instant record of what you're looking at, you're no longer limited by the biological eye that sort of just dumps everything to your brain on the order of 30 times a second. You now can collect light through the telescope for a full second, for a minute, for an hour if you can hold things steady enough. And this allowed folks to do some really, really fantastic science with this new eye. In fact, it really allowed us to even move into spectroscopy, where we take the light of objects, break it up through a prism or a diffraction grating, and study the elements and motions of what's going on. This is what Edwin Hubble and William Humason did on Mount Wilson. Their work in 1929, kind of the first observational evidence of what we now consider the Big Bang Theory, although you could make an argument that previous to that, Vesta Slipher's work showed this as well. He just didn't have the data, the distance data that Hubble and Humason had. In 1978, Vera Rubin, the observatory's namesake, used a telescope attached to a camera to measure the spin rates of galaxies, and notice that, gosh, every single galaxy we look at is spinning way too fast for the gravity that it should have. They should all be flying apart, but they're not, so we're missing some mass, and this is the beginnings of dark matter. The last new eye that we get was a replacement for the film canister, which is the CCD. Or I guess we can use CMOS today as well. But the charged coupled device, a quantum bit of electronics that is a digital camera. The digital camera revolutionized astronomy in a way that getting a brand new eye does. We now aren't limited to taking a picture on a photograph. The chemicals are out of the loop in terms you don't have to worry about development chemicals. You don't have to worry about negatives. It's a lot easier to put these in spacecraft, for example. The original, like the Kodak Instamatic, the instant Polaroid, the self-developing things that were out for such a long time. That's really similar to some of the things that were developed for some of the early space photography, because they still had to use, chemical developer and things like that. But this now lets us do something like, I don't know, the Hubble Space Telescope. And with a CCD, we can take an arbitrary number of pictures for an arbitrary amount of time, and we can do things like let the Hubble Space Telescope point at a patch of sky for 14 days straight and produce this image, the Hubble Ultra Deep Field. The 1, 2, 3, 4 objects kind of running down the middle that have diffraction spikes are stars in our galaxy. Every other speck of light there is a whole nother galaxy with hundreds of billions of stars in it. It's absolutely astounding. And CCDs, a CCD camera, a digital camera attached to a telescope, is basically the standard equipment of your observatory now, ranging from the half-meter telescope that we have on the roof of our science building at Monmouth College, all the way up through the James Webb Space Telescope. In fact, I mean, everybody has a digital camera in their pocket now. It's hard to find something that isn't a digital camera anymore. But hold that thought. I want to also now turn to a side of astronomy that benefited from these eyes that isn't part of this normal narrative, and that's survey astronomy. And sometimes it's seen as the less glamorous companion of astronomy. And this is the idea of just going out and marking down what and where everything is that you can see. Probably the earliest, most famous star catalog is the Star Catalog of Hipparchus, established back around 150 BCE. Basically, he just went out at night and it's like, there's a star, there's a star, there's a star, there's a star, and recorded it. In China, 2 centuries later, Zhang Heng did basically the same thing, went outside, like, there's a star, there's a star, there's a star, recorded it. Al-Sufi, known in the West as Azofi, did this during the Islamic Golden Age. Moving back in the beginning of the European Renaissance, Bayer did this. And then Flamsteed in 1725 did the very first one using a telescope. And actually a lot of star designations are still the Flamsteed designations. Whenever you have kind of like number constellation, that's a Flamsteed designation. The constellation Greek letter is a Bayer designation. So, I mean, we're still using things that these folks came up with long, long ago. So we can see that the telescope has come into it, but once we get the ability to photograph things, we get all sky surveys. We get surveys that are designed to try to take a picture of the entire sky. Now, they can't do it all at once. The first real attempt at this that they pulled off was at Mount Palomar, the POS survey, the Palomar Observatory Sky Survey. Took about 5 years to do, and they used the 48-inch telescope at Mount Palomar in Southern California, and they took 2 images of every patch of sky through this telescope, one through a red filter, one through a blue filter. So you can find the POS blue and the POS red now. Down there in the lower left is basically the tiling pattern for that the POS observed the sky in. And in the upper right are the blue and the red images of the Pleiades cluster, which you can see a really nice image down in the lower right. That's a modern digital image of it. But no bonus points for guessing which is the blue and which is the red picture there. But POS is still being used today. When we had access to digital cameras, an effort was made to redo this in a different way. And this is the Sloan Digital Sky Survey. The Sloan Digital Sky Survey ran for about 10 years, right around 2000 to 2010. I will note that the Sloan Digital Sky Survey is still going on. They repurpose the telescope and do a new survey with it every so often. We're into kind of the 5th generation, but we're really talking about the very first Sloan Digital Sky Survey. And its goal was basically to make a digital color picture of the entire sky viewable from New Mexico. It had 5 color filters ranging from near infrared to near ultraviolet. The telescope there is about 2.5 meter. It's actually exactly 2.5. It's kind of a funny telescope. I really like it. It's got this big square thing on it. That's a wind baffle because it actually is completely exposed. That's a pier sticking out off of the Sacramento Mountains in New Mexico. And way down below is basically a cliff that goes down to the city of Alamogordo. Overall, over these 10 years, Sloan scanned the sky and recorded about 60 terabytes worth of data. So that's, 61 terabyte hard drives or 32 terabyte hard drives. Here's the kicker, though. By doing a survey, you're doing far more science, or you're enabling far more science than you ever thought you would. Sloan was originally built as an extragalactic survey. It was specifically designed to study galaxies and the distribution of galaxies and quasars in space, but value added. It did incredible work on galaxies as it was designed to do, but it also made fundamental discoveries about stars, about nebula, about the structure of the Milky Way. It was an asteroid discovery and observation engine. It made observations that go into pinning down cosmological constants involving dark matter and dark energy. And something on the order of 10 to 20,000 papers have been written with Sloan data, and somewhere between 500,000 and 1 million papers have cited Sloan data, making it the number 2 most cited astronomical telescope behind the Hubble Space Telescope. So out of kind of modern telescopes, from a scientific volume perspective, only Hubble has been more productive than Sloan. In fact, the Sloan Digital Sky Survey is why I'm here talking to all of you today. I worked on the Sloan survey while I was a graduate student. I dug through Sloan looking for comets, and I found them. No one else had spent any time looking for comets until I came along. And in the process of doing my dissertation work, I discovered why no one had done it yet, because it was hard. That's why they gave me a PhD for it. I found a whole bunch of comets. I did discover a comet. Unfortunately, it was already known as an asteroid, so there is no comet Solontoi zipping around. Sad. Oh well, whatever. It's fine. I did get to image Comet 67P, and I was studying that long before. That was the target of the European Rosetta mission that actually landed a little tiny probe on it. So I was into that comet before it was cool. Why am I talking about this? Well, at the time we were doing this, around 2005, I got involved with what is now the Rubin Observatory. We were planning and discussing the next generation of all-sky survey. So all of this was done with Sloan with a digital image taken by a 2.5 meter telescope. What could we do with an 8.5 meter telescope that makes a digital movie? And that's the idea behind the Rubin Observatory. It's in the southern hemisphere. It's in Chile, and it's going to image the entire southern sky about 1,000 times in 6 filters. Again, from the near infrared to the very near ultraviolet. It will essentially, in this cadence, it will take only about a week to image the entire southern sky that's viewable. It will basically produce a Sloan Digital Sky Survey every single week. And it will enable time domain astronomy. The universe is not a static and unchanging thing. Yes, you could watch a galaxy from now till the day you die, and you won't see it turn at all, but there are plenty of stars that pulsate, asteroids, comets, explosions, supernova. There is a lot of things that change on human appreciable timescales, and we want to get at them. Also, this is going to be a fantastically deeper survey. Sloan goes down to around 21 magnitude. Rubin will go down to 27th magnitude. What does this mean for an observation? I have this little kind of put together here. Here is an image of the sky from the POS film survey from the 1950s. It's just blue. It's just blue and red superimposed, so you don't get a whole lot of color information on things. But that's a patch of sky as observed by POS. This same patch of sky was observed in the Sloan Digital Sky Survey, and this is what Sloan produced. We have color. We picked 3 out of those 5 filters to make an RGB image, but you can see it's a much deeper image than what POS had. For Rubin, this patch of the sky, since it's in the northern hemisphere, might not actually be observed by Rubin. Plus, we don't have that data yet. But the Canada, France, Hawaii telescope has observed that same patch of sky at Rubin depth, and this is what you're going to get from Rubin. Much, much deeper. So Rubin, the mission behind the Vera Rubin Observatory is to build a very well understood, well characterized, well calibrated, basically a system that we know inside and out to produce an unprecedented astronomical data set to study the deep and dynamic universe, make this data accessible to a diverse community ranging from scientists to school children who want to explore the universe. That's what we really want to do with it. And we're going to get into how we're going to do this, but like Sloan, there were some drivers that guided the construction and design of the Rubin Observatory. And there were kind of 4 pillars of science that we wanted Rubin to be able to accomplish. First, it needed to make progress and observe things to tell us more about the nature of dark energy and dark matter, some of these big cosmological mysteries. Second, it was going to map the Milky Way. It needed to observe a lot of the stars in the Milky Way at very high precision, very accurately, so we could really map out the Milky Way. Design the time domain lets it explore the transient universe. In other words, all the stars that pulsate, the stars that flare, the stars that explode. And in those transient events, we're going to actually carve out the things that move, comets, asteroids, and what have you, because the 4th pillar of science that Rubin was designed around was to inventory the solar system. We're going to come back to the science in a moment, but first let's talk actually about this machine itself. So what is our new eye? The Rubin Observatory, and it's really weird for me to be talking about the Rubin Observatory now in the present tense. I'll just say that right out. It's kind of, I get the giggles whenever I have to talk about it in the present tense, because, for 20 years, I've been telling people this is going to be amazing. And guess what? It is amazing. So here's our new eye. We're going to combine the following components to make this brand new eye. We're going to take a specially designed 8.5-meter mirror, actually an 8.4 mirror primary with a secondary and a tertiary in there as well. We're going to mount in it the world's largest digital camera that measures in at somewhere around 3.2 billion pixels. We'll put the whole thing together into a 300-ton telescope, put it inside a mountaintop fortress, run a fiber cable from Chile to California to deal with 500 petabytes of data. there's 1,000 terabytes in a petabyte. So that's 500, that's 500,000 hard drives right there. And involve the effort and work and thoughts of thousands of people across the globe. The most recent Rubin meeting I was at, I believe we had 19 different time zones represented. So yeah, try to schedule that. Um, let's go through this a little bit. The site, the Rubin Observatory, is located at Sierra Pachon. It's up just shy of 9,000 feet above sea level. It's in the Andes. It's just up the mountains from the city of La Serena in Chile, which is a bit north of the capital, Santiago. You can't see it in the picture I'm showing here, but just over the ridge in the other direction are a few other telescopes. Most notably, I believe Gemini South is right here, as well as a few of the US Aura installations. So it's a fairly large astronomical complex up here, which is nice. It means that there were like, roads that trucks could drive already built and things, because you definitely want some trucks to haul that stuff up there. The telescope itself, this is an image of the Simone Survey Telescope, is fast. It can slew 90 degrees in 9 seconds, which is impressive considering it weighs 300 tons. It can go from one position of the sky to another and be still enough to take an image in 5 seconds. And whenever I talk to an astronomy club, someone always asks me what the F ratio of the telescope is. It's an F 1.234. So it's a very, very fast telescope. I have a little, not an animation, an actual video of the mount moving. This thing is moving in real time. The plane wave telescope that we have on the roof of the physics building doesn't slew this fast. And this is 300 tons. So it moves fast. The mirror is a really interesting design mirror. It's a triple mirror. So it's actually technically, it's called a Paul Baker anastigmat, which is the design. It's designed specifically to compensate for a number of the aberrations that you get from using mirrored surfaces. What we've got here is the light comes in and hits this large outer primary, bounces up to the secondary, which until the extremely large telescope that the Europeans are building gets its secondary. It's currently the largest mirror of its type in the world, but it'll only hold that record until the Europeans get their mirror out of the cooking machine. It bounces back down to a tertiary mirror that's actually being ground into the primary. This is the mirror blank undergoing grinding at the University of Arizona's Mirror Lab. There's a reason why so many of our large telescopes are exactly 8.4 meters in diameter. That's because that's the biggest blank that the University of Arizona has at their Mirror Lab. The telescope, right after it was actually fired before the grounding, this was the blank for the Rubin Observatory's main primary mirror, was actually cast back in 2008. So this is a lot of the Rubin team at that time kind of posing with this, big hunk of glass. The camera, the theme of today is big. The camera is big. It's 3.2 billion pixels, or 3,200 megapixels. The camera itself is this teal and black device. So the camera itself is about the size of a car. Here it is in the clean room with a bunch of the clean room techs. There's the business end of the telescope. And this is a 1-to-1 scale representation of the actual CCD. That's the focal plane. That's the detector. That is made up of many 4K by 4K CCD chips there. It's a big thing, and you can fit it at the focal point. It swallows the sky at about 10 square degrees at a time, which means you can fit about 7 full moons across one Rubin image. What does 3.2 billion pixels mean? Well, it means that no one is ever going to look at all the pixels ever taken by Rubin. I can show you a Rubin image on the screen, and you would not be seeing the true pixel values. To display a single Rubin image, you would need about 1,500 HD TVs, or since television technology keeps advancing, if you have access to ultra high definition televisions, you would only need 400 of them. to see one image. So if you wanted to be crazy and actually make a tile wall big enough to display one Rubin image, there it is mounted on the side of a building, obviously a drawing. If you were really crazy and wanted to print a Rubin image at kind of this normal 300 DPI, you need enough paper to cover 3 tennis courts. Again, the theme is big. You can fit, it's going to be swallowing the sky massively. There we go. There's our 7 full moons fitting across one field of view. As far as angular resolution, not that you could point such a telescope at a terrestrial target, but the angular resolution will be such that you can spot a golf ball at 15 kilometers. What does that mean in terms of space stuff? This right here is an image taken by the Canada-France-Hawaii telescope to a similar depth as the Rubin Observatory will do. The brown line that we've added to this image is the width of a human hair scaled to the angular size being held at arm's length. So just a hair held at arm's length is that brown line right there. The type of resolution that we get is much, much smaller than your hair held at arm's length. So this is going to be very similar to when Rubin is up and running at full resolution here. The frightening thing is that every single speck of light in this image down to that resolution is going to be automatically detected, analyzed, and recorded. Over the survey, Rubin will observe billions of objects and make trillions of measurements, producing about 20 terabytes of data every night. All in all, Rubin taken together, if you take every astronomical data set ever produced, the Rubin data set is about 10 times larger than all of them together. Now we know that this is even a very, very boring research astronomer at times. Actually, I teach for a living, but don't enjoy looking at column after column of numbers. So we're building in to Rubin as we go all the education and public outreach tools to give people access to this data who don't want to deal with several trillion rows of spreadsheets. While this is all going on, Rubin, remember, is focused on the time domain. So anytime Rubin notices something in the sky that has changed through difference imaging, you take a picture of the sky, and then later you take another picture of that same bit of sky, you subtract one picture from the other, and if nothing has changed, they cancel out. If something has changed, you get a dot. Anytime Rubin sees a dot, it's going to send out alert to the interested members of the astrophysical community. And we estimate that Rubin will be sending out about 10 million alerts a night. So please do not hit the subscribe all button unless you absolutely hate your inbox. This includes things like asteroids, supernovas, flares, just anything that changes, really. Are all going to be going and being alerted. And the goal is that these alerts actually go out within 60 seconds of the observation. So this is a prompt data product. So this is even before the data has gone through the entire processing to make it photometrically usable. These detections and alerts are going out because another way of thinking about Rubin is that it is now the world's spotter scope. You have these amazing very narrow field of view telescopes that can get exquisite images like the James Webb Space Telescope, the current generation of very large 30-meter class telescopes that are in development. Rubin's going to find a heck of a lot of things that need follow-up from ground-based and space-based telescopes. So that's the purpose of these alerts, that something exciting happens and the world can turn their telescopes to really figure out what they are. Now, this is all kind of pointing to doing astronomy in a different way. And to quote Vera Rubin herself, I was more interested in the question than the answer. I decided at an early age that we inhabit a very curious world. Asking questions is, and will be even more so, the most important thing to do in science, particularly going forward here. Traditionally, astronomy has been very, very data starved. Surveys like Rubin are changing that. It's no longer the case that, gosh, I want to study this type of object. I'm going to apply for some telescope time and cross my fingers, I got it. They gave me time on the telescope. All right, I'm going to be ready to go. In 2 months, I get to look at my object. 2 months go by, I'm ready, and it's raining. I don't get any data. I myself lost an entire weekend of 3.5 meter telescope time in New Mexico to a hurricane. We say that again, New Mexico, hurricane. I have really bad luck. So, Rubin is going to deliver positions, magnitudes, variability information on everything in the southern sky down to just crazy faint limits. So what do we expect to do? And to horribly mangle a quote from John F. Kennedy, ask not what data you need to do your science, ask what science you can do with your data. Maybe you're interested in mapping out the Milky Way. The distribution of stars in the Milky Way give us a clue as to the formation and evolution of our own galaxy. We can see tidal streams left behind by little dwarf galaxies that the Milky Way has swallowed up into itself. So say we want to do this. It's very much like doing, they sometimes even call it galactic archaeology. Well, if you're interested in studying the Milky Way, Rubin will provide you with 20 billion stars in the galaxy with which to do your galactic archaeology. Maybe you're interested in exploring the transient sky, exploding stars like supernovas, variable stars like RR Lyraes or Cepheids or Delta Scutis, or maybe just new things that are just weird and strange. Well, subscribe to the alert brokers and Rubin will tell you about 1 to 10 million of each of these things each and every night. Well, let's think big. What about cosmological puzzles? Maybe you're interested in things like the mystery of dark matter and dark energy and just the cosmic history of the universe itself. Well, to do so, we need to study galaxies. And these galaxies, we look for them being gravitationally lensed, where one nearby galaxy is distorting the light from a distant galaxy. Again, when you're looking so far back, the universe is amazing in the fact that it also gives us a time machine. It's not just a space machine, but it's a time machine. It's much better to think about a galaxy that's 8 billion light years away as we're actually looking at a galaxy as it was 8 billion years ago. So by looking at distant objects, we get to see how the universe was then and can compare it to how the universe is now. And say you want to do that? Well, Rubin will give you 20 billion galaxies to study, spanning about 10 billion years worth of universe's history. Okay, that's getting way too big. Let's focus down. Plus, it's my own topic. What if you're interested in the solar system? I don't know why you'd be interested in the solar system. I don't know. But anyways, if you're interested in the solar system, maybe you're interested in inventorying the solar system. What do we mean by that? We mean really finding all of the solar system small bodies, the asteroids, the comets, mainly the asteroids in the main belt between Mars and Jupiter, the Trojan asteroids that orbit along with Jupiter, out beyond the orbit of Neptune, the Kuiper belt objects, and way out beyond our detection limits, the long period comets that live out in the Oort cloud. Maybe you're interested in these, and by surveying the sky, we can start completing our collection and understanding how many of these things are there. What's more, in studying this, we learn some really fantastic things about the solar system. So why am I showing you a picture of duckies? Well, if you've ever heard of the friendly floaties, we're going to talk about the friendly floaties. If you haven't heard about the friendly floaties, today's your lucky day, because we're going to talk about the friendly floaties. The friendly floaties, there's an analogy coming, don't worry. The friendly floaties were the result of a shipping container accident in the North Pacific in 1992. In 1992, a shipping container went overboard full of bathtub toys. It spilled open, and the bathtub toys have been circling the globe ever since. Within 2 years, they started making landfall in Alaska, and within a decade, they made it as far as Scotland. By tracking where and when these bathtub toys washed ashore, oceanographers were actually able to map out the currents of the oceans and where the oceans trap things, where the oceans transport things in a way that they had never been able to do before. Why am I talking about the friendly floaties? The asteroids and comets of the solar system are our own cosmic friendly floaties. They mark out the places in the solar system that the motions of the giant planets during the formation and evolution of our solar system have not disturbed. If we want to understand how our solar system formed and how our solar system got to the way it is today, we need to understand the relic populations. I'm not knocking the major planets. They're fantastic. They're interesting, they're unique, they're special. But Jupiter alone doesn't tell us about the history of our solar system. We need these tiny bits of rock and ice that have been preserved since the earliest times in our solar system. That, and maybe you've got a soft spot for that day 65 million years ago where the dinosaurs bravely gave their lives so that our squirrel-like ancestors could, give mammals a chance at this whole ruling the earth thing here. Have we been hit by asteroids in the past? Yes. Will we get hit in the future? Yes. Are we going to get hit by anything we know of right now? No. But the dinosaurs aren't around to save us anymore, so we might want to find out where they are so that we can throw Bruce Willis at it. On the chart here, this is just, I looked this up right before the talk. Within the next 24 hours, these are the 3 closest things that are going to buzz by us within 24 hours. These are 3 asteroids ranging in kind of a few tens of meters across. The closest one will come within about 3 times the distance between the Earth and the Moon. So don't have to worry about any of these, but as they get closer and closer, you never know. The other thing that you get by just surveying everything is that you get the chance to see rare and exotic things. Only about 10 years ago, we discovered that there's comets hiding in the main belt. These are asteroids that periodically erupt like comets and get very bright and produce a coma and tail. There's very active study right now on these so-called main belt comets. Also, only within the last decade, we've confirmed detected extrasolar comets. These are comets from another star system that were lost by their star system, trundling through the galaxy and just kind of blew by us. 1I and 2I were the first 2 found, and we'll get to it. But if you've been following kind of astronomy news over the summer, we have a 3rd one now, 3I Atlas, but I'm going to save that one for later. What this means is that by surveying the solar system, what's Rubin going to do? So say you want to study the solar system. Rubin will discover, not observe, but discover 5 million main belt asteroids. There's about 1 million known today. And that same sort of increase in objects is throughout this. So basically, for every main belt object that we know today, Rubin will discover 5. For every interstellar object known today, Rubin will discover 5. For every Kuiper belt object known today, Rubin will discover 5. These are estimates, of course. We can't see the future. This is assuming our statistical understanding of these populations is correct. That's a whole lot of numbers, and I hate carrying a lot of numbers with me. So all I ever really remember when I talk about this is take every observation that's ever been made of a comet or an asteroid. Rubin, over 10 years, will take 20 times that number of observations. So yeah. And as I said, there's already tools designed for Rubin outreach and education. No data in it yet. But we have tools, we've things that are working that are going to go into the schools, into high schools, into colleges, into activity groups. It's fantastic. We want people to have access to Rubin. Now, overall, these points that I've been making point to something, this change in astronomy that I said, that the future of astronomy, or at least the future of astronomy that's enabled by Rubin, is data-driven. We are about to enter an age of extremely abundant high-quality data, and knowing what and how to ask questions is probably going to be the most important thing. Working with Rubin will make people as scientists think differently. And probably it's this last tagline that I'm most excited about. My PhD thesis used a telescope whose creators had no idea somebody would ever use it for comets. Probably some of the most interesting Rubin science we haven't even thought about yet. I like to kind of think about it as panning for gold, only instead of panning for gold, you're sifting through 10 years of 40 billion science objects for things that interest you. I say again that I get kind of giddy when I talk about Rubin because I've been involved in it. And there's some things that like every now and then remind me that this is a big, big, big project. Like, for example, we have a Lego minifig. I mean, that's cool. And as the minifig is saying, it's huge. So let's talk about Rubin as of today. Earlier this year, Rubin released this time-lapse video of 10, because they finished 10 official years of construction and completed the actual building of the observatory. Little animation here with probably too loud music. And it's a movie, not an animation. I'm sorry. At the time, that statement was true. Because after that movie had been made in April of 2025, the first photon was taken through the full camera. Prior to this, there was a camera on the telescope called the commissioning camera, which was a small scale version of the Rubin camera. I believe ComCam is now going to be mounted on the auxiliary telescope for calibrations. And when that first signal from the sky made it through the system, the folks who were in kind of the inner circle of the Rubin builders who were in attendance were very, very excited. And they are still very, very, very excited. This first photon event was followed later this summer, actually just back in late June. On June 23rd, Rubin held its first look media event, where during the timing of commissioning after the camera was on, they took a image of the sky enough times that it was representative of what Rubin will do over its 10-year survey. You could sign up and host or attend a Rubin First Look watch party. Somewhere around just shy of 400 locations were registered. About 150,000 people attended. I held a very, very small one in Monmouth. It's very, very small because Monmouth itself has a population of about 10,000, and that includes the students at the college. So it was small by design, but we have data. This is part of the Rubin First Look, and it's beautiful. Just galaxies and galaxies and galaxies. It's actually over kind of by Virgo, I think. This image is amazing. And while I'm tempted to just leave this here for us to stare at it, you're welcome to, you can find it, you can download it, you can make your wallpaper. I have it as my wallpaper. You know the drill. This image here, though, I want to point out something. This isn't the first Rubin image. This is a very small portion. Remember how big that camera is? That whole image is just this little bit, a little bit smaller than the full moon portion of the full Rubin First Look image. And the only way to really look at the Rubin First Look image is through some sort of kind of a scrolling thing, because if you zoom out far enough to see the whole thing, you miss a lot of the lovely detail. And if you zoom in enough to see the lovely detail, you miss the grandiose, just wow, there's so much stuff there. So again, big, big project. I let movies talk for me some point because this is all brand new data. I mean, this came out in late June. So this is just kind of panning around the first look. In this panorama here, there's about 10 million galaxies imaged in this first look image. And that may seem like a lot, but that's only about 0.05% of the 20 billion galaxies that Rubin will actually observe during the main survey. That's the whole image. That's the telescope footprint. So it's actually kind of two there on the whole thing. What's kind of cool about that image is that while that's the only fully processed image from Rubin, it's already navigable online. Skyviewer.app is the link to basically using Rubin as your planetarium. That's the main kind of sky server for Rubin for just exploring the data. And people are already doing things. Someone's already gone through and made like a sonification of the Rubin image. So as you drag your cursor over the screen, it makes a nice little bell tone that represents the color and magnitude of the pixels that you're dragging your cursor over. So people are already doing amazing things with this. Speaking of amazing things, this image is highly processed, and actually it's missing something. To make a really, really pretty picture like that, you've got to remove all of these little rainbow streaks. Again, they're rainbow streaks because we're taking 3 images taken at different times, coloring them red, green, and blue, and stacking them together. These are asteroid streaks. This has to do with stuff in our solar system that's whizzing by in the sky and getting in the way of the very beautiful picture. There's a reason why my fellow astronomers call my field, the asteroids, call it the vermin of the sky, because they're always just getting in the way of them studying their stars and galaxies. I turn that around and say that their stars and galaxies get in the way of me studying my asteroids. But because all of those asteroids have to be identified and removed for people to study stars and galaxies, it means that Rubin detects automatically all of the asteroids there. And as a result, in this first image, they detected a whole lot of asteroids, but I'd like to highlight the fact that 2,104 of them were discovered. So what we'll notice is that in these images, we see a lot of little moving objects. There are a lot of asteroids in the Rubin first look image. You don't see any of them because they've been removed to make it pretty. But in removing them, we discovered about 2,000 brand new, never known before asteroids. A handful of them, I think about 7 of them were near Earth objects, and a couple of them were Kuiper Belt objects. So this is just kind of the discoveries of them over it's about a total of 10 hours of observation spread out over about 6 or 7 nights. Again, in the sky, it's going to zoom out and show you where this is in the solar system. By and large, most of those are here in the main belt of the main asteroid belt, but some of them stretch all the way out into the Kuiper Belt as well. And as Rubin goes, it's going to just be sweeping around, finding all of these things. So what did we think of the first look? It was a resounding success. This is Dr. Željko Ivezic doing what is now known as the Željko dance. Željko is also my PhD advisor. He's the project scientist for Rubin Observatory. What do I mean by successful? I mean, any metric. My thing is, like, the New York Times gave it 5 pages, which I think is kind of cool. I don't remember the last time something sciencey got 5 pages in the New York Times. The moon landing, that definitely got more than 5 pages. But seriously, from a science perspective, in late June, after the first look image, the science community got access to the engineering test data. And people are already doing science and writing papers on just the engineering test data. The engineering test data is being used. It's already created the very first Rubin citizen science project, comet catchers, where you can log in and look for asteroids that are exhibiting cometary activity. From my own standpoint, I got the opportunity to be involved with the very first official science paper written using the full LSST camera data. And this was on the 3rd interstellar comet, 3I Atlas. While we're going through all this, 3I Atlas was discovered, and we're like, well, wouldn't it have been kind of cool if Rubin had been pointing in that direction while it's doing its science validation? And someone kind of said, well, it kind of was. So we had a lot of discussions with people who were behind the embargo wall because they're still figuring things out. They don't want to serve up data to the public that's not correct yet. And we kind of came together over the course of the week like Voltron and found a couple dozen observations of this interstellar comet in the Rubin science test data and wrote a paper and it's currently being refereed and should be published soon, I hope. So that's kind of cool. So even though like the telescope is still being tested, it's already generating brand new science. And I think that's fantastically cool. Um, because this whole thing is just fantastically cool. And I think I will leave you with the words of Vera Rubin. The joy and fun of understanding the universe we bequeath to our grandchildren and to their grandchildren. With over 90% of the matter in the universe still to play with, even the sky will not be the limit. It's an immensely interesting and exciting universe out there, and we desperately want you to explore it with us. So thank you.
Thank you. All right, let's open it up for any questions from the audience or anybody online. Last questions for episode back. Back row.
What about the Northern Hemisphere? Any
Uh,
plans
yeah, if you've got a location and a big pocketbook to build a Rubin North, talk to me after this meeting and we can set something up. No, actually, we get a little bit of the Northern Hemisphere. We cover in order to sample. Am I still sharing or did I turn everything? Oh, I turned everything off. Good, I think. Oh, here we go. Stop sharing. There we go. I'm like, hold on, where's the Zoom window? And there's just, all right. The location in Chile, we can see a little bit into the Northern Hemisphere. What's the, not too far. The main excursions that we do into the Northern Hemisphere is to follow the plane of the galaxy up to kind of map out a little bit of the North Galactic spur. And then because we're definitely interested in solar system objects, we follow the ecliptic as it arches up into the Northern Hemisphere as well. I was smart enough to bring up a page with all of the Rubin number fact sheets. It can go to it can go up to about plus 12 in declination, is about as far north as Rubin can look.
Great.
Have any of the constellation of satellites affected the telescope?
Yes and no. In some ways, yes. Particularly if you're interested in finding the near Earth objects. That's the science that's probably going to be impacted the most by them, because that's when, like, you have to find near Earth objects. You want to really look kind of right around twilight. You want to be looking just after sunset and just before sunrise, because that's the only time that you can kind of look along the path of Earth's orbit. And that's really where that population can be observed. Unfortunately, that's also the time when satellites that are basically a giant refrigerator with a foil sheet on them are very reflective to sunlight. And the first generation of Starlink satellites would actually blind Rubin, but talking with, there were some agreements made, and the current generation of Starlink satellites, while it will wipe out any data along its path, no longer actually just kind of ruin the entire pixel image. But yeah, that is an ongoing problem for any sort of major survey telescope, is that particularly early in the evening and and then late in the morning, you get a lot of satellites overhead, particularly these constellations. We do what we can to mitigate it.
Okay.
how are the data accessed? Do you need to have a protocol in place to access the data, or can anyone access it? If I came up with a project, would I be able
Yeah.
to?
Okay. So I'm going to speak. This is we're recording this. So I'm going to say this is off the record because I'm not on exactly the status. I think what it is right now, and this is the regulations have evolved, because if you notice, we have both the initials of the NSF as well as the DOE. So we're both a project of the National Science Foundation as well as the Department of Energy. So there's certain proprietary things on there. For the science access, the numbers, the values, the things like that, that is accessed through something called the Rubin Science Platform. That if you are affiliated with a institution or educational facility in the US or Chile, or with some of the international partners that have made in-kind contributions, you can access it. Otherwise, that access will be provided after some amount of proprietary time has gone by. I don't know for a fact on that right now. I think the idea is that this is beyond just what's served on the Sky server. So those are actually down to like the pixel values. If you wanted to get like the raw data and do your own reductions and things like that, you would need the Rubin Science Platform. The Sky Viewer app is going to have a surprisingly large amount of information on it. But yeah, I don't know. I think that the answer to that is actually going to evolve. I know it's actually evolved quite a bit over the past few years. So please keep whatever I'm saying. If it turns out that I'm catastrophically wrong on any of those remarks, no, don't throw things at me, please.
So am I understanding you don't actually sign up for time on it like the Hubble as a researcher?
No, it is it's completely automated.
Okay.
Yeah, Rubin, and that's actually what I've been involved with Rubin for the past couple years. Is I've been in a group from the Solar System Science Collaboration that has been assessing different cadence schemes of how Rubin is going to observe the sky and the impact on which of these are really good for observing the solar system and which ones aren't so good. Actually, do I have that here still? Yes, actually, let me go back to a screen share because it's a really neat movie that Lynn Jones made, and it's utterly fantastic. That kind of just shows this idea of the cadence, but it's an automatic. It's automatic. The only input is that there will be times, and they're working out it right now. So do you see two kind of ellipses that represent the sky?
Yes, yeah.
All right. So what you're going to see is the little dot whizzing around is showing where the Rubin footprint is. And this is just chunking along. So that was night 43. This is the simulated cadence for night 83. It's just rolling through the hours. The different colors represent different filters. So what I've been doing for the past few years in terms of Rubin is assessing these things for does it observe a lot of it? Does it discover a lot of asteroids or not? So yeah, this is and then this is a little bit later on that. It always avoids somewhere on here is usually where the moon is, so you don't point the telescope at the moon because the moon is bright. But so that's the idea of the cadence, and I think my computer is running a little slow right now. But I just really like those. When Lynn started making those diagrams, we all discovered that they're very hypnotic to just watch the cadence go and go and go and go and go and go. So yeah, you don't apply for it at all. It's a survey telescope. You can ask the interface for the science platform right now has a way of basically doing kind of some check boxes and kind of search criteria. And otherwise, you can dive into it and write your own kind of SQL query. And but most of us actually just access it through Python. Actually, that is something that is 100% public today. The actual pipeline that reduces data for Rubin is on GitHub. So if you're crazy enough, you could actually use the Rubin reduction software on your own images if you wanted to. I'm not sure how well that would work, but you could certainly give it a go.
Okay. I just want to pause for anybody online with a question. We'll give you just a moment to hit the button if you have a question. All right, and if not,
Yeah, so regarding that cadence, does it do, oh, you said 6 filters?
Yes.
From all at once, or does it do
Uh,
different
no.
filters for a section of the sky and then come back?
Yeah, so I think again, this is what I've been working on, so I get the cadences confused. I think right now the cadence is it takes a 30-second exposure, moves, 30-second exposure, moves, it goes through that, and then it either repeats that in the same filter or it switches filters and repeats that. It takes about a week to get the whole sky in the filter set.
Okay, and you said it moved very quickly. How quickly can it switch filters?
Don't know that number offhand. I do know for a fact that actually the filter raft, because fitting 6 giant plates of glass in there is difficult.
Yeah.
Only 5 out of the 6 filters are loaded at a time. I know the filter change works, and it's rapid enough that they can do it in the middle of the night without a substantial amount of downtime. The 2 filters that get the least use, the filter that's out in the ultraviolet, doesn't get used all the time because it needs very, very dark conditions for. And then I think the filter that's the second of the 2 infrared filters gets used a little bit less. So for the most part, it's a very similar filter set that what the Sloan Digital Sky Survey used, except for it has one extra infrared filter that goes a little bit beyond what the Sloan Z filter did.
Bob,
Yeah.
How exactly will Rubin help understand what dark matter is? Is there a way that it will actually image it or
No, but
some
yeah,
method of?
so it's mainly through. So the example I would like to give on that is that by studying when you have a large concentration of galaxies, that's a big ball of mass. Under our understanding of gravity works by basically a geometric warping of the space around the masses. So distant galaxies, as the light from those distant galaxies goes past this big blob of mass, it gets bent a little bit. We actually can demonstrate this during a solar eclipse. The stars nearest the sun are actually out of position a little bit because the starlight passing by the sun gets bent just a scotch. It's a very accurate way of determining masses and distributions, and you can compare that directly measured gravitational mass with things like the luminous mass and then the assumed luminous mass. So just the mass that's in stars and gas and dust and lost socks and everything else that we know of, to really just pin down what sort of percentages. In terms of finding out what dark matter is, right now, our best bet is either we have a fundamental problem with gravity, which no one has been able to make a correction to gravity that dealt with dark matter that also don't make the Earth spontaneously explode. Possibly we've kind of handed the what is dark matter over to particle physics, and actually 2 out of the 3 experiments on the main beam line at the CERN particle accelerator have at least a component of a dark matter search going on right now. But mainly just by observing all sorts of galaxies, you can make these mass measurements. You can also see the distribution and the evolution of galaxies over cosmological times, so you can weigh how important this dark matter contribution is to that. And I'm kind of dancing around this because keep in mind that I study rocks in space. My science I can go and hit with a hammer. If I have a big enough budget, I can send somebody to actually hit an asteroid with a hammer. So
okay, we'll take one more question.
no worries.
Are there galaxies that don't have have excessive rotation that do not have dark matter?
Well, if they have excessive rotation, that's the hallmark of them having too much mass. And this idea of just too much mass is where we get dark matter from. We found galaxies actually the other way around. We have found galaxies that have very little kind of star gas and dust in them. And they're just utterly dominated by whatever this missing mass is. I'll be honest, I thought when I got to graduate school, someone would clue me in. I was like, here's what dark matter really, we don't really believe any of that. Here's what it, sadly, no, we're kind of stuck with it right now until someone makes a fantastic discovery that one of these particle accelerators or someone comes up with a brilliant piece of theoretical physics. I wish I could tell you more, but if I could tell you more about dark matter, I'd have a medal from the King of Sweden, which is what you get when you win the Nobel Prize.
Well,
It's a darn good question, though.
okay. Well, thank you. This is a really good presentation, and thank you for your time.
Fantastic.
And all the questions that we had here tonight too, so.
Fantastic.
And Dr. Solontoi, I'll connect with you tomorrow with an email.
Great. Fantastic. I had a great time. Thank you so much for inviting me to talk to you this evening. Had a great time. So great questions. Sounds like it was a good audience. So.
Yeah.
We have your number now.
Okay. All right. No worries. Yep. You can share if someone has a question they want to ask me, feel free to give them my email. If I don't respond to you, it's not that I'm hiding. Our campus email does have a little bit of a habit of being a little bit overly aggressive with the spam filter. So I go into my junk mail once every week or so to double check. So if you don't hear back from me right away, I'll see your email eventually.
You got a room full of nerds that completely understand.
Oh yeah. So,
all right. Have a good evening. Thanks.
You too. Thank you again for having me here.
Thanks, Mike. Yeah.
Bye-bye.
And we'll just take a moment. Anybody else who wants to fall offline, you can do that. Anybody in the room want to leave, you can, but you're certainly invited to stay with us. And we probably will have another half hour or so of meeting time, going through some pub events, some outreach. We'll take a 1 minute break, then we'll jump it back into it.